So the flow rates of hot and cold fluid stream running through a parallel flow heat exchangers are 0.2 kg per second and 0.5 kg per second respectively. The inlet temperature on the hot and cold side are 75 degrees Celsius and 20 degrees Celsius respectively. The exit temperature of hot water is 45 degrees Celsius. The individual heat transfer coefficient on both sides are 650 watt per meter square degree Celsius. Calculate the area of heat exchanger. So we have this parallel flow heat exchanger question, and they have given the hot and cold water flow rate as 0.2 kg per second and 0.5 kg per second, and also the inlet temperature of both hot and cold side, right? It has 75 degrees Celsius and 20 degrees Celsius. Also the exit of the hot water is also given 45 degrees Celsius. We have to find the area of the heat exchanger. So this is the figure according to the given condition. We have a parallel flow arrangement. We have know the cold water and hot water is moving in parallel, and the inlet temperature TC1 of the cold water 20 degrees Celsius. Correspondingly, the inlet temperature of the hot water is 75 degrees Celsius. Similarly, we have the outlet of the hot water as 45 degrees Celsius, but we don't have the outlet temperature of cold water. Okay, let's look how to solve this problem. So first of all, write the given condition. Mass flow rate of the hot water is 0.2 kg per second. Mass flow rate of the cold water MC 0.5 kg per second. TH1 inlet of hot water 75 degrees Celsius. TH2 45 degrees Celsius. TC1 20 degrees Celsius, and they have also given the heat transfer coefficient. Okay, that is individual heat transfer coefficient as 650 watt per meter square degree Celsius, and it is both, it is same for both inside and outside. Okay, so inside and outside means both hot water stream and cold water, there will be two surface, right? Inner and outer. There will be a wall separating there should be some sort of division, so that's how inner and outer, and it's both same, that individual heat transfer coefficient same, which is 650 watt per meter square degree Celsius. So the basic thing to solve is basic theory or basic idea behind this is the heat lost by the hot water is gained by the cold water. We know how the heat exchanger work. Simply the heat lost by the hot water is gained by the cold water. That's how the hot water temperature decreases and cold water temperature increases. So we know the heat lost, or enthalpy of heat lost, which is mcp delta T. So you can apply separately the equation. Here we do not have TC2. Okay, we don't know the values of TC2. So in order to find that, before that we can find Q, because you can be find from both hot fluid equation and cold fluid equation, but we only have the parameters of the hot fluid equation. So I will be using mh into cph into th1 minus th2, because we have all those values. But on the other side, we don't have TC2. That's why I can apply the cold water equation to find Q. So I will be applying hot water equation. So thereby I get Q as 25.122 kilojoule per second. So then applying the basic equation, heat loss is equal to heat gain. So equating, we can find TC2 as 32 degrees Celsius. Okay, we have finally TC2. So now we have the logarithmic mean temperature difference in Lmtd equation. Theta m is equal to theta 1 minus theta 2 by ln theta 1 by theta 2. Now theta 1 is the difference between th1 and tc1, while theta 2 is the difference between th2 and tc2. Okay, so applying the equation, we get Lmtd or theta m as 29.12 degrees Celsius. So this is the plot of temperature versus length for this parallel flow heat exchanger. We have theta 1, theta 2, th1, tc1, th2, tc2. So this is the final equation. We know the final equation for Lmtd. Q is equal to UA Lmtd or UA theta m. Before that we need to know U. Okay, so it can be applied from the formula 1 by U is equal to 1 by Hi plus 1 by HO, and there was L by K, but the space, the medium between is not considered, because as there is no data is given, we are neglecting that. So only 1 by hi plus 1 by ho. So we have 1 by u equal to 1 by hi plus 1 by ho. We know 1 by hi and ho. From that we can find u as 325 watt per meter square degree Celsius, and substitute that equation, substitute that value in the equation. Q is equal to ua theta m. From that a is equal to 2.66 meter square.